Why does the characteristic polynomial encode eigenvalues? Let's remember back to what eigenvectors are. An eigenvector, v, is just a non-trivial solution to this equation. The matrix times the vector is lambda, a scalar, times that vector. And in this case, that number, that scalar lambda, is what we call the eigenvalue. Well, here is a neat thing. The roots of the characteristic polynomial are exactly the eigenvalues of the matrix. And that's so important, I've just got to write it down. The roots of the characteristic polynomial of M are exactly the eigenvalues of that matrix M. Well, why is that? Well, let's suppose we've got an eigenvector v with corresponding eigenvalue lambda, meaning we've got a non-trivial non-zero vector v and some scalar lambda satisfying this equation mv equals lambda v. Well, subtracting lambda v from both sides, this just means that mv minus lambda v is equal to the zero vector. Then I could rewrite lambda v in the following way. I could write this as mv minus lambda, the identity matrix, times v equals the zero vector. Then I could factor out a common factor of v here, and I could write this as m minus lambda times the identity times the vector v equals the zero vector. Now what's important about this is that I've got a non-trivial vector v, which I've multiplied by m minus lambda times the identity, and I'm getting the zero vector. What this means is that v is some non-trivial vector in the null space, or the kernel, of m minus lambda times the identity. And because v is a non-trivial element of this null space, or this kernel, that means that m minus lambda times the identity for this eigenvalue lambda is not invertible. And because it's not invertible, that tells me that the determinant of m minus lambda times the identity must be equal to the number 0. Or in other words, it's telling me that lambda is a root of the characteristic polynomial of this matrix M. And this argument can be reversed. What I mean is that I can run this argument exactly backwards. I can start at the bottom and end up at the top. I can begin with lambda being some root of the characteristic polynomial of this square matrix M, and lambda being a root of that characteristic polynomial means that the determinant of m minus lambda times the identity matrix, this determinant vanishes. Now, if this determinant is equal to 0, that means that this matrix is not invertible, but this is a square matrix which isn't invertible. That means I can find some non-trivial vector v in its null space. That means that I can find a solution to this equation for some non-zero vector v. M minus lambda times the identity times the vector v is the zero vector. But then just expanding this out and rearranging, I can find a non-trivial solution to this equation. The matrix times the vector v is lambda times v, and this lambda started out life as a root of the characteristic polynomial of M. So if I start with the root of the characteristic polynomial, I get an eigenvalue. And if I start with an eigenvalue, I get a root of the characteristic polynomial. And that means that the set of eigenvalues and the roots of the characteristic polynomial, they're exactly the same thing. And the key fact to making this work is to relate information about the eigenvalues of M, which are related then to the non-trivial solutions to this equation, mv equals lambda v. If I've got a non-trivial solution to this equation, a non-zero v making this true, well, that means I've got some non-trivial element of the null space of m minus lambda times the identity. And if I've got a non-trivial element of the null space of this square matrix, well, that tells me information about the determinant of this square matrix. If this null space is non-trivial, that means this matrix is not invertible. That means this determinant vanishes. And after all, the determinant of m minus lambda I, well, that's just the characteristic polynomial of M. So I should warn you that you shouldn't go around telling people that the eigenvalues are defined to be the roots of the characteristic polynomial. You don't need all this fancy machinery of determinants and characteristic polynomials just to talk about eigenvalues. I mean, eigenvalues and eigenvectors are really more fundamental notions, and we don't need all this fancy machinery to talk about them. But it is the case that the characteristic polynomial and eigenvalues are certainly related. And in practice, I mean, if somebody comes up to you and asks you to find the eigenvalues of some matrix, a very reasonable strategy is for you to compute the characteristic polynomial of that matrix and then find the roots of that characteristic polynomial.